Welcome to Amplified Education, your exam prep friend. Today we are looking at work energy exam questions. Please pause the video and try the question on your own. The question reads, a 5 kg box starts from rest and is accelerated across a horizontal surface for a distance of 10 meters. At the end of the 10 meters, the box reaches a velocity of 15 meters per second. A force F is applied to the box at an angle of 20 degrees to the horizontal. The coefficient of kinetic friction between the box and the surface is 0,125. The first question says, draw a free body diagram for all forces acting on the 5 kg box. And so 1.1, let me just pull this down a bit. Okay, I think this should work. All right, so 1.1, remember it's a free body diagram, and so the body of the object is represented using a dot, and there is definitely a normal force and a force that is applied at an angle. There's definitely friction, kinetic friction, and there is Fg, is the gravitational force. And I always prefer drawing the components of the force applied in my free body. So I'm going to draw another free body on the right-hand side with my normal force there and Fy there, Fx there, Fg there, and the kinetic friction Ffk. Now we could label those forces. So Fn, we know Fn represents the normal force. And Ffk represents kinetic friction. And then F just represents the applied force. And then your Fg represents the force of gravity. Okay, that is your 1.1. 1.2 says define normal force. I'm just going to write this here so that I save the space on the right-hand side for calculations. Normal force is a perpendicular force exerted by a surface on an object in contact with it. Then 1.3 says we must write an expression for the normal force in terms of F. Now, in order for us to determine the normal force, is we have to consider the fact that the force applied is acting at an angle, and that force that is acting at an angle is providing a lifting force, which causes the box to be slightly in less contact with the ground. And there's also an applied horizontal force called Fx, as shown in the free body diagram. So then for the normal force, we can see that Fy and Fn is acting in the same direction. So we could say Fn plus Fy is equal to Fg, and then Fn is equal to Fg minus, not plus, minus Fy. Now, to find Fy, Fy would be equal to, all right, that would be Fg minus F, the force applied, sine Let me write that properly. Sine theta. Okay, that is F sine theta, right? Which is equal to 5 times 9.8 because FG is mg. So 5 times 9.8 is 49 minus F sine 20 degrees. And that would be the expression of the normal force in terms of F. Okay. The next question says write an expression for the horizontal component of the applied force in terms of F. Right, that is 1.4. So that is F of x. All right, or Fx is equal to the force applied cosine theta. All right, remember this is the horizontal component. And if you don't remember how to find the components, right? Remember, if that particular force is acting that way, the horizontal force should be acting to the right, and the vertical force should be acting upwards. But what's important about this is that if you go back to your trigonometry, this side at the bottom of this triangle would be the adjacent side, and that would be the hypotenuse side, and that's the opposite side. And so to find the opposite side, which is Fy, you would say opposite side over the hypotenuse, right? So you'd say O over H is equal to sine theta, and then A over H is equal to cosine theta. And that's pretty much how we find those expressions for the force applied. Okay, so that would be pretty much what that is about. And so your Fx is F cosine 20 degrees. Let's see, let's just erase this so that it's not all clustered here. All right, perfect. All right, now 1.5 says we must use energy principles to calculate the value of F. So obviously here we are going to use the work energy theorem, and maybe before we use it, let's state it. So the work energy theorem states that the work done by a net force on an object is equal to the change in the kinetic energy of the object. Of the object. So to that's the statement. That's pretty much what the work energy theorem says. And so to write that as a formula, you would say work net is equal to the change in the kinetic energy, which would be the work done by the applied force, in this context, the horizontal component, Fx, plus the work done by the frictional force, which is Ff, K is equal to a half mvf squared minus a half mvi squared. Now we know that the object started at rest, so we are not really interested in the initial kinetic energy, right? And if that's the case, then the work done by Fx would be F cosine 20 degrees multiplied by 10, which is the displacement that the box covers, cosine 0 degrees, plus, now the work done by friction, remember, we do not have an expression for friction yet. So to find an expression for friction, it would be FFK equals UK, multiply that by Fn. We do have UK, which is 0,125, and we do have an expression for Fn, which is 49 minus F sine 20 degrees. If we multiply the 49 by the 0.125, 0.125 times 49, we get 6,125 minus 0,125, multiply that by sine 20 degrees, you will get 0,043 F, and that would be an expression for the kinetic friction. So plus 6,125 minus, all right, 0,043 F, and you multiply that by the distance of 10, right? Right, cosine 180 degrees, because remember, friction does negative work on the object. So we're going to multiply that by 180 degrees to get -1. Then we equate that to a half. The mass of the object is 5, and its final velocity after 10 meters is 15 squared. Right, we just have to simplify all of that. So we're going to say cosine 20, multiply that by 10, and we're going to get 9,4. All right, so that's 9,4 F. Then we're going to distribute that and say plus 10 times 6,125. And we're going to get 61,25 minus 10 times 0.043. And we're going to get minus 0.43 F, right? And that is equal to 0.5 times 5 times 15 squared, right? After the equal sign, we're going to get 562.5. And then we're going to isolate F so that we can solve for F. So we're going to say 9,4 minus 0,43. We get 8.97 F. And let's bring everything to the other side. It's transposed there. That's 562.5 minus 61.25. And then we get 501.25. And so F is equal to 501.25 divided by 8,97. Then we're going to get 55,88 newtons. All right, so that would be your answer. And then the last question, which is 1.6, I'm going to do it here on the left-hand side. It says the angle at which the force is applied is now increased. How will increase in the angle of the applied force affect the frictional force? Right, increase, decrease, or remain the same. And so the frictional force should decrease. Okay, because if you are providing more lifting force by increasing the angle of the applied force, then you are causing the box to be in less contact with the ground, which decreases the frictional force. So in other words, if theta increases, all right, then cosine theta should decrease. If cosine theta decreases, right, Cosine theta decreases because you've increased the angle. Then your Fy as well. Your Fy, your lifting force, your Fy, which is calculated using sine, should increase. Okay. So maybe let's not even think about cosine theta, but let's think about sine theta rather. Okay, so let's say sine theta would also increase. If sine theta increases, right, then the lifting force Fy should also increase. If the lifting force Fy increases, remember the expression for normal force was normal force equals Fg minus Fy. So if this increases, then the normal force decreases. If the normal force decreases, then what will happen is that, remember, the frictional force FFK is directly proportional to the normal force. So if the normal force decreases, then the frictional force should also decrease. And that would be the answer. I hope that helps. Thank you.